This is section 3.6, but I want to go back and do some more problems from 3.5 also. So do that first. 3.5, number 25, find the equation of the tangent to the curve y sine 2x equals x cosine 2y at the point pi over 2, pi over 4. So differentiate implicitly. This is a product rule. First times derivative of the second, y times cosine 2x times 2, plus second times derivative of the first, sine of 2x, derivative of y is 1 dy dx, equals derivative of the right side, x times negative sine 2y times 2 dy dx. There's supposed to be a dy dx here also because I'm differentiating 2y, and when there's a y, I need a dy dx. Plus second function, cosine 2y times derivative of the first, which is x. Okay, put all the dy dx's together. So I move this one over here and I move this one over here. Factor out the dy dx. Sine 2x plus 2x sine 2y equals cosine of 2y minus 2y cosine 2x. Okay, this comes over here. So dy dx is cosine 2y minus 2y cosine 2x over sine 2x plus 2x sine 2y. Okay, and now I plug in pi over 4 every time I see y, and pi over 2 everywhere I see x. So pi over 4 goes here, here, and here. Pi over 2 goes here, here, and here. So this is cosine pi over 2, 0, minus pi over 2 cosine of pi divided by sine of pi plus 2 pi over 2 is pi, sine of pi over 2. Okay, that's 0. That's negative 1 over 0 plus pi times 1. That's pi over 2 divided by pi, which is pi over 2 times 1 over pi, 1/2. So y minus y1 equals m times x minus x1, or y equals a half x. Okay. Okay, 3.519, sine of xy equals cosine of x plus y. So differentiate this, cosine xy, then by the chain root times the derivative of the inside, which is a product. So first times derivative of the second, dy dx, plus y times 1, equals negative sine x plus y times derivative of the inside, 1 plus dy dx. All right, distribute over here. So if I distribute negative sine x plus y minus sine x plus y dy dx, distribute here, x cosine xy dy dx plus y cosine xy, very messy. So put all the dy dx's together. So this comes over here, that goes over there. So factor out the dy dx, x cosine xy plus sine x plus y equals negative sine x plus y minus y, because that comes over, minus y cosine xy, divide both sides by this mess. So dy dx is negative sine x plus y minus y cosine xy divided by x cosine xy plus sine of x plus y. 27, find the equation of the tangent to x squared plus xy minus y squared equals 1 at 2, 1. Differentiate implicitly, 2x plus product root. At the original, there was a negative, so make it plus negative x times y. So the first function is negative x. So negative x times dy dx plus y times negative 1 minus 2y dy dx equals the derivative of the right side is 0. Okay, and rather than solving for dy dx, you're allowed to just plug in. So everywhere I see x, put a 2 there, there. Everywhere I see y, put a 1, which is there and there. It makes it a little bit easier. So that's 4 minus 2 dy dx minus 1 minus 2 times 1 dy dx. Okay, so that gives me 3 minus 4 dy dx equals 0. So dy dx equals 3/4. So that's a slope. And that's the point. So y minus 1 equals m 3/4 times x minus 2. That's the equation of the tangent line. 33, come up with the equation of the tangent line. Y squared equals 5x to the 4th minus x squared at the point 1, 2. 2y dy dx equals 20x cubed minus 2x divided by 2y. Plug in 1 there, 2 there. So the bottom is 2 times 2. The top is 20 minus 2, 18 over 4, or 9 over 2. So y minus y1, y minus 2 equals m 9/2 times x minus 1. A quick derivation of the inverse trig derivatives. Okay, you're not responsible for the derivation, just to be able to use it. But here's a derivation: y equals inverse sine of x. Rewrite it as sine of y equals x. Cosine y is dy dx equals 1. Dy dx is 1 over cosine y. Draw a triangle. Sine is opposite over hypotenuse, x over 1. Do a little bit of Pythagorean theorem. That's radical 1 minus x squared. So dy dx is 1 divided by cosine of y. So it's 1 over adjacent over hypotenuse, radical 1 minus x squared divided by 1, or 1 over radical 1 minus x squared. So the derivative of inverse sine is 1 over radical 1 minus x squared. Inverse cosine. Y equals inverse cosine of x. Take the cosine of both sides. Cosine y is x over 1. Differentiate implicitly. Derivative of cosine y is negative sine y dy dx equals 1. dy dx is negative 1 over sine y. Again, draw a triangle. Cosine of y is adjacent over hypotenuse. That makes this radical 1 minus x squared. So dy dx is negative 1 over sine of y. Sine is opposite over hypotenuse, radical 1 minus x squared over 1. So negative 1 over radical 1 minus x squared. So bottom line, derivative of inverse cosine is negative 1 over radical 1 minus x squared. Then inverse tangent, y equals inverse tangent of x. Take the tangent of both sides. Tan y is x over 1. Differentiate implicitly. Secant squared y dy dx is 1. Divide by secant squared of y. So dy dx is 1 over secant squared y, which is cosine squared of y. Draw my triangle. Tangent is opposite over adjacent. That would make the hypotenuse radical 1 plus x squared, Pythagorean theorem. And so dy dx is cosine squared of y. So cosine is adjacent over hypotenuse. So 1 over radical 1 plus x squared, square it, 1 over 1 plus x squared. So derivative of inverse tangent is 1 over 1 plus x squared. You're not responsible for any derivation. You just want to use it. So put this on your formula sheet. Put this on your formula sheet. And put this on your formula sheet. Don't worry about inverse, secant, cosecant, and cotangent. We're not going to do those. Okay, so a couple more problems. Take the derivative of y equals inverse tangent of x squared, chain rule. So it's 1 over 1 plus this thing squared, 1 plus x squared, squared, and then by the chain rule times the derivative of x squared, which is 2x. So 2x over 1 plus x to the fourth. Okay, 52, differentiate arc cosine radical x. Arc cosine means the same thing as inverse cosine. Okay, so the derivative is negative 1 over radical 1 minus radical x squared times the derivative of radical x. That's like x to the 1/2. So 1/2 x to negative 1/2. So this gives me negative 1 over radical 1 minus x. This 2 comes here, and I have a radical x here. And you're allowed to put these into 1. So negative 1 over 2 radical x minus x squared. Okay. And this one, y equals x inverse sine x plus radical 1 minus x squared. Okay, so y prime is first times derivative of the second plus second times derivative of the first. Derivative of x is 1. Derivative of this is 1/2 1 minus x squared to negative 1/2 times negative 2x. This comes out to be x over radical 1 minus x squared minus x over radical 1 minus x squared plus inverse sine of x. Final answer is inverse sine of x. Okay. All right, so we're starting 3.6 now. What is the derivative of the natural log function? Derivative of log functions, page 218. What is ln x prime? Okay, so we will change it to an exponential. Y equals ln x, exponentiate both sides. E to the y is x, and then I differentiate implicitly. E to the y dy dx equals 1. Dy dx is 1 over e to the y, but e to the y is just x. So dy dx is 1 over x. So bottom line, derivative of ln x is 1 over x. Okay, what if I have a log to any other base, log base b? Well, we have a property of logs that I can rewrite this as ln x over ln b. So think of this as a coefficient of 1 over ln b. Therefore, y prime is 1 over ln b times 1 over x, 1 over x ln b. So the derivative of log base b of x is 1 over x ln b. And the best base is base e. Okay, so on page 218, derivative of ln x is 1 over x. If you have any other base, derivative of log base b of x is 1 over x ln b. Put those in the formula sheets. Clearly, we like base e the best because you don't have to multiply by anything extra. Finally, we're ready to prove the power rule. Okay, so y equals x to the n. Take the log of both sides. ln y equals ln x to the n. This is logarithmic differentiation, which we're doing in this section also. N comes in front. Ln y equals n ln x. Differentiate implicitly, 1 over y dy dx equals n times 1 over x. Multiply both sides by y. Dy dx equals n y over x, but y was x to the n. So x to the n divided by x to the 1. Dy dx is n x to the n minus 1. So finally, we prove the power rule that the derivative of x to the n is n x to the n minus 1. Okay. One other thing I want to know about derivatives. Okay, it turns out find a derivative of ln absolute value of x. Well, absolute value of x is the same as x if x is greater than 0. Okay. But you have ln negative x if x is less than 0. Well, what's the derivative of ln negative x? Chain rule. 1 over negative x times derivative of negative x, which is negative 1. You still get 1 over x. Okay. So that tells me that the derivative with respect to x of ln absolute value of x equals 1 over x. Okay. We actually don't use this that much now, but we will later on toward the end of our course. But the derivative of ln absolute value of x is also 1 over x. Okay. Now for a bunch of problems. 3.6. We're going to look at. First thing I want you to notice about logs, keep in mind ln of a, b is ln a plus ln b. That makes some problems a little bit easier. So suppose I have g of x is ln x e to the negative 2x. So you can make it easier by making this ln x plus ln e to the negative 2x. And I know that ln e back to back cancel out. So I have ln x minus 2x. So the derivative is 1 over x minus 2, which is much easier than if I were to just go 1 over x e to the negative 2x and then do the chain rule. Okay? So we will have the chain rule involving natural logs also, no question about it. Okay, right. Okay, problem 3. F of x is sine of ln x. So chain rule, the derivative is cosine ln x times the derivative of ln x, which is 1 over x. So final answer is cosine ln x over x. Okay. How about f of x equals ln 1 over x? Well, you treat this as ln x at a negative 1, and then bring a negative 1 in front, negative ln x. Therefore, derivative is just negative 1 over x. Okay. 13 is a good problem. It helps you set up another problem later. It's got ln of 2y plus 1 to the 5th over radical y squared plus 1. You can do the chain rule as is, but it's going to be very messy. You have to go 1 over all this, and then times the derivative of the inside, which involves a quotient. Much better to use property of logs. So before I start differentiation, I can write this as ln 2y plus 1 to the 5th. And since there's a division here, it's minus ln of y squared plus 1 to the half. And then the half gets to come in front. 5 comes in front. So 5 ln 2y plus 1 equal minus 1/2 ln y squared plus 1. Now I'm ready to differentiate. G prime of y is 5, constant multiplier root, 1 over 2y plus 1 times the derivative of 2y plus 1, which is 2, minus 1/2. Derivative ln y squared plus 1 is 1 over y squared plus 1 times the derivative of y squared plus 1, chain root, which is 2y. So final answer is 10 over 2y plus 1 minus y over y squared plus 1. Okay, t of z is 2 to the z log base 2 of z. That's a product rule. So the t prime of z is first times derivative second, derivative log base 2 of z is 1 over z ln 2 plus second function log base 2 of z times derivative of the first, derivative of 2 to the z is 2 to the z ln 2. And a side mark. For my z's, I'll generally make a mark like this, because if I write it too fast, you can't tell the difference between a 2 and a z, and I'm too lazy to make my z's look like so. right? So my z's will also be like that. Okay, and this is a reminder of what I mentioned earlier. The derivative of ln x is 1 over x. The derivative of ln negative x by the chain rule is 1 over negative x times negative 1. It's also 1 over x. So therefore, the derivative with respect to x of ln absolute value of x is also 1 over x. All right, 25, y equals ln absolute value of secant of x. So I go 1 over secant of x times the derivative of secant x, which is secant x tangent x. These guys cancel out. So y prime is tan x. Therefore, y double prime is the derivative of tangent secant squared x. 33, y equals ln x squared minus 2x plus 1 at the point 3, 0. So dy dx is 1 over x squared minus 3x plus 1. Then by the chain rule times the derivative of the inside, which is 2x minus 3. 2x minus 3 over x squared minus 3x plus 1. Okay, now I plug in x equals 3. 2 times 3 minus 3. 3 squared minus 3 times 3 plus 1. That's 6 minus 3 over 9 minus 9 plus 1. 3 over 1, 3. So y minus 0, y minus y1 equals m3 times x minus x1, x minus 3. All right, now we're going to tackle something called logarithmic differentiation. Okay. So logarithmic differentiation. Y equals square root of x minus 1 over x to the fourth plus 1. So the game we're kind of playing is, we're saying, I wish there was an ln. If there was an ln, then I can start the process just like I did over here. Okay, so if you want the ln, just put in the ln. Difference, however, is that the left side isn't y anymore, it's ln y. But that's okay, as I'll show you. So now this is ln x minus 1 over x to the fourth plus 1 to the 1/2. And now I can use my property of logs, bring the half in front. ln of a quotient is the difference of the logs. So 1/2 ln x minus 1 minus ln x to the fourth plus 1. Now I differentiate implicitly both sides. So this becomes 1 over y dy dx. It's always going to be like that. That never changes. Then this is going to be 1/2. So 1 over x minus 1 minus 1 over x to the fourth plus 1 times the derivative of x to the fourth plus 1, which is 4x cubed. Okay. And then normally what happens at the very end is you multiply both sides by y. So that isolates a dy dx. But you don't leave it as a y. You write what the original y was. So the original y was like that. Okay. So I'm going to write my final answer as 1/2 radical x minus 1 over x to the fourth plus 1, and then times this extra factor. So 1 over x minus 1 minus 4x cubed over x to the fourth plus 1. Okay, so some reminders of how I differentiate. If you have a variable raised to a constant, like y equals x squared, that's just a power root. Y prime is 2x. If you have it reversed, if you have a constant to a variable, like 2 to the x, that's an exponential. So the derivative is 2 to the x ln 2. If you have a variable to a variable, like x to the x, then you have to do this logarithmic differentiation stuff. Okay, so let me show you how to differentiate variable to a variable. Do not do the rule for exponentials. Do not do the rule for power functions either. So in other words, do not go x to the x minus 1. So how do I differentiate x to the x, problem 43? Take the natural log of both sides. So ln y equals ln x to the x. Once I have the ln, that x gets to come down in front. The left side's always going to be 1 over y dy dx, just like it was for this problem. That never changes. Differentiate the right side, product rule, x times the derivative of the second, 1 over x, plus second function ln x times the derivative of the first, which is 1. X's cancel out. Then multiply both sides by the original y. Okay, so dy dx is y, but write what it's equal to, x to the x times this extra stuff, which is 1 plus ln x. Okay. Another logarithmic differentiation, 3.6, number 49. Y equals tan x raised to the 1 over x. Okay, so that's a little bit funny. So take the ln of both sides. That brings 1 over x down. In fact, I can put it as a fraction. So ln y is ln tan x over x. This side's always going to be 1 over y dy dx. This is a quotient. So bottom times derivative of top. Derivative of top is 1 over tan x times the derivative of tan x, which is secant squared x, minus the top, ln tan x times the derivative of the bottom, but that's just 1, all over x squared. Okay, and then multiply both sides by y. That's always the next step. So these cancel out. dy dx is y, the original function, which was tan x to the 1 over x. X times 1 over tan is cotan, secant squared, minus ln tan x all over x squared. Okay, so that's the way that one goes. Mm-hmm. 3.639. Okay, now we're going to do this by logarithmic differentiation because it says so. We can do this without logarithmic differentiation. You can just do the product rule. But this was a section to practice the logarithmic differentiation. So ln both sides. Then you use the property of logs. ln of a product is ln of the first plus ln of the second. The 2 comes down, the 4 comes down. Differentiate implicitly, 1 over y dy dx. It's always like that. Then the derivative of this is 2 times 1 over x squared plus 2 times 2x plus 4 times 1 over x to the 4th plus 4 times 4x cubed. And then you always multiply both sides by y, but you don't leave it as y. You multiply the actual y, which was this. So dy dx is the original x squared plus 2 squared times x to the 4th plus 4 to the 4th times this extra stuff, which is 2 times 2x, 4x over x squared plus 2 plus 16x cubed over x to the 4th plus 4. That is equivalent to what you would get if you just did the product rule and the chain rule. 45, y equals x raised to the sine x. Okay, so that's a variable to a variable. Take the ln of both sides. That allows sine x to come down. 1 over y dy dx. This is always 1 over y dy dx. Product rule. First, sine x times the derivative of the second, which is 1 over x, plus second function ln x times the derivative of the first, derivative of sine is cosine. Multiply both sides by y. So dy dx, but you don't write it as y, you write what it was. X to the sine x times this extra stuff, sine x over x plus cosine x ln x. Okay. One of the problem I wanted to go back on was 3.449. That was a little bit tricky to do that one. It's very messy. So y equals square root of 1 minus secant t. That's 1 minus secant t to the 1/2. So y prime is 1/2, 1 minus secant t to the negative 1/2 times derivative of the inside, which is negative secant t tangent t. Clean it up. So negative secant t tangent t over 2 radical 1 minus secant t. Okay, this has a coefficient of negative 1/2. So take out the negative 1/2 for the second derivative, and now it gets even more messy. But there's a negative 1/2 in front, so negative 1/2, there it is. And now I just differentiate secant t tangent t over radical 1 minus secant t. So from the quotient rule, the denominator is just the square of this, 1 minus secant t. But how about the numerator? So bottom times derivative of the top. Derivative of secant t tangent t is secant t times derivative of tangent t secant squared t plus second function tangent of t times derivative of the first secant t tangent t minus the top secant t tangent t times derivative of the bottom. Derivative of the bottom is 1/2, 1 minus secant t to the negative 1/2 times derivative of the inside, which is negative secant t tangent t all over this. So this mess, it can be simplified. It's not worth doing it. We'll just say that we've done enough for that one. That was 3.449 also. But for the most part, this was section 3.6.